more examples. So here we give priority to the examples involving energy, as we didn't solve examples they are involving energy and power in a circuit. So a battery of EMF 12 volts and internal resistance 0.5 is connected across a resistor in series with a low resistance ammeter. When the circuit is switched on, the steady reading of an ammeter is 1 ampere. When the circuit is switched on, the steady reading of ammeter is 1 ampere. Calculate the rate of consumption of chemical energy of a battery. Ukwambia rate of energy hii ni power, kwa sababu power ni unavyokuambia rate ni something per time, so energy per time hiyo ni power. Second, the rate of dissipation of energy inside the battery. So how much energy is lost as heat by the battery itself. It means due to the internal resistance of the battery itself. The rate of dissipation of energy in the resistor. So you should also find the energy that is lost as heat in the resistor that is connected outside the battery. Okay, power output of the source. Solutions are simple, as you can see here. They're just statements. If you're speaking of the rate of consumption of chemical energy, this means the amount of energy that the battery produces, because the battery produces the chemical energy. So the rate of consumption of chemical energy, it means the energy that the battery is offering, the power for this case, because it's the rate of consumption of chemical energy. So it's the power that the battery is offering. As I said, when you are dealing with cells, and when we're dealing with cells, the power that the cells can deliver, the power that the cell can give, as here the power that the chemical energy that the battery is producing, we use this formula of V times I, where V becomes the EMF of the battery. But in our question we are given the EMF is 12 and the current is 1 ampere. So simply the power, the chemical energy produced by the battery is 12 times 1, which is 12 watts. Watts because it is power, and we were asked the rate of consumption of energy, which is power. Second, the rate of energy dissipation inside the battery. When we are speaking of heat dissipation, energy lost as heat, when we are dealing with resistors, we use the equation of I square times R. But since we are told inside the battery the resistor that we use is the internal resistance, so I is the current that passes across the internal resistance, which is the current that passes across the battery, I, which is 1 ampere, because they are connected in series, the current is the same, squared times the internal resistance, which we are given is 0.5, and we get 0.5 watts. The third equation, the third question that we are asked is the rate of dissipation of energy in the resistor. We were not told about the resistor here, but this question gives us a hint that there was a resistor that was connected in this circuit. So how do we get the resistor? I said earlier that the energy E, the formula E is equal to I R plus I R, means that the energy, the EMF, the force that is produced by the battery is splitted into force that will be used to drive current through external resistors, and plus the force that will be used to drive current through the battery itself, the internal resistance. Therefore, to get the power, the force that passes only to the external resistor is equal to the force that is generated by the whole battery minus the one that the battery itself consumes. It means the remaining one, all that is remaining, is passing to the outside the resistors. Similarly, here when he speaks of rate of dissipation of energy in the resistor, it's the same concept as this one, that the total power that the battery can offer is equal to the power that goes to the resistors externally plus the power that goes to the internal resistance that is lost as heat in the internal resistance. So to get the power that goes to the resistor, the rate of dissipation of energy in the resistor is equal to the total power that is produced minus that one that is lost in the internal resistance. So the total power we know is 12 watts, and the power that has been produced inside the battery, the lost as heat, is 0.5. So 12 minus 0.5, we get 11.5 watts. So power output of the source. Power output is how much the source is now offering for the external component, that after it is able to produce a certain amount of power, which is this one, the total chemical energy that it can produce, there is some part of that is used by the battery itself and is lost as heat due to the internal resistance. So all that is remaining is the one that the battery can give as output, okay, the one that the battery can offer to the external resistors. So similarly, it's just like the previous question. So this is the total power that the battery can offer, but this is the power that the battery itself loses as heat due to the internal resistance. So the ability that it can give as output is the remaining power, which is 11 watts. Again, we have another example. A heater is designed to operate with a power of 100 watts on a 100 volt line. It is connected to two resistances of 10 ohms and 5 ohms as shown in the figure below. One is connected across it, one is connected in series. What is the power output of the heater? What does this heater give as the power output? So resistance of the heater. Okay, resistance of the heater. First we can find the resistance of the heater ili tujue how much power is the heater losing as the the heater itself. So we know that power is equal to V squared over R. We remember this, is it? Yes. So from here we can get the resistance, that if the electric kettle can operate at a power of 100 watts, okay, and the voltage that can operate to give those 100 watts is 100 volts, so we can get the resistance of the heater itself operating. So these values ambazo unapewa operating ndo unatumia kutafutia resistance of the heater when it is operating now. So V square, which is 100 squared, the voltage square, because the resistance is V square over P, 100 square divided by the power, which is 1000 watts, you get 10 ohms. That's the resistance of the heater. So similarly, we have to find how much power is the heater losing, so that we can know how much can it give as output. Okay, yeah. So to know the amount of power lost as heat, we first have to know the current that is passing through the heater, and it is not simply the 100 volts. It's not simply the 100 volts divided by the resistance. No, is in operating values, so you should not use them to calculate current or no. Hizi ni ratings ambazo zinakuja na heater, kwamba hii heater inaweza ikioperate at 100 watts, inatakiwa iwe kwenye 100 volts line, resistance yake ni hapa. So usije ukajichanganya kutumia hizi operating values zilizopewa kutafutia current, sababu simply mtu anaweza kusema current si hapa 100 volts, nimepewa resistance ya heater, then I can get the current that is passing the heater. No, these are operating values. Sasa hiyo current wako umeipata ni current kama heater ikiwa peke yake. Inapokuwa connected to resistors, kuna redistribution of that energy, so kata current inakuwa inabadilika. So to get the current that is passing through here, so we have to find the effective, because they are in series, so the current that will be passing is the same for here and here. So okay, there are so many ways you can use to get the current that passes through a heater. So first we are required to find the equivalent resistance of the whole circuit. So first we start with the parallel circuit. We have the resistance of the heater as 10 ohms, and here we have 5 ohms. So effective R1 R2 divided by R1 plus R2. We remember when we find the effective resistance, so we get 10 over 3 ohms. So total circuit resistance, we have this equivalent here, 10 over 3, then it is in series with 10 ohms. So in series you just add plus 10, you get the effective resistance for the whole circuit, because we are not told if the battery has internal resistance, so we neglect. The total effective resistance of the whole circuit is therefore 40 divided by 3 ohms. So the current in the circuit because we are using the total resistance and we are using the total volt that the battery can offer, then we get the total current that is passing through the whole current, the circuit. So it is 7.5 amperes. But again, here we use our principal current divider. So in such cases is when the principle of current division can help us. See, so we know that our formula of current divider, we know that if we want the current passing through the heater, according to our principle of current divider, that we have the current, you remember, current of the heater is equal to the total current in this whole circuit times the ratio of the resistors. But you remember that the ratio of the resistor, I said, unlike for potential divider, resistor that stays on top is not for the one that we are looking for. We are looking for the current of the heater, but here on top stays the resistor of the other resistor, which is 5, the other one that they are sharing, not this one, because here we are looking at a point where current is dividing between this and this. So on top it will be stay 5 ohms, as you can see here. Down here the total 5 plus that, it divides the total current in the circuit of 7.5 amperes. So the power output of the heater comes to be 2.5 squared times 10. So you find this as the amount ile ambayo itakuwa lost kwenye heater. Amount ile ambayo itakuwa lost kwenye heater, nilikwambia sehemu yote ambayo tunatumia resistors tunatumia formula I squared R. So natumia current inapita kwenye heater ambao ni 2.5 squared times resistance of the heater ambao ni 2 ohms. Tunapata power ambayo inakuwa lost kwenye heater ni 62.5 watts. So we have another example here. You can check this through and solve it on your own. Just remember, hapa kuna concept ya specific capacity. Just remember the principle of heat produced by the kettle is equal to the heat taken by the water, and you remember this formula for specific heat capacity. I hope you remember that, then you can try that on your own.